In our previous video, we talked about how we can find a rate based on the rate law, and we're able to find out the different orders of the reactants based on the experimental data. In this video, we're going to talk about that rate constant, that letter K, that is found in every single rate law. So once you find the rate and you have the rate law filled in, you can find the rate constant. Okay? In order to find the value of the rate constant, you can choose any of those trials. So if we come back to our previous information, you can take any of these trials here, and if you have the orders correct, it doesn't matter if you use trial 1, trial 2, 3, or 4. You simply plug those numbers into your rate law here, and so you plug in the rate. So here's our rate here. You plug that in here. You take each of these concentrations, and again, you plug them in here. And what's the only thing you don't know is you don't know the rate constant. So you basically plug all those values in there, and then you solve for K. So if the rate law were rate equals K times the concentration of A times B, so in this case, they're both first order. It's a second order reaction overall. To solve for K, we would simply divide both sides by the concentration of A and B, which would result in this equation here. Okay, and again, using the data from trial 2 in that first example, not the example I just showed you, you basically plug those numbers in. Here's where I really want you to notice, okay, is that when we talk about the rate constant, this is one time where they will give you credit or not give you credit if your units are wrong. In general, they don't care about units on the AP test. But with rate constants, they do, because those units can change. So notice what I did here is I have 2 molar per second. So there's my molarity on the top. It's molarity per second. That was my rate. Okay, again, I'm using example 1, not example 2 here. So from this example right here, I'm using this data. So I'm using 1. So it's changing initially by 1 molar per second is how you say that. Okay, and so notice the way that I write that. I write that as, or I can't remember, I think it was the second trial. So 2 molar per second. So the molarity is on the top and the seconds are on the bottom. And then we've got, again, the concentration of A, which is in molarity, and the concentration of B, which is in molarity. So you've got a molarity on the top and molarity times molarity on the bottom, which is really molarity squared. Okay, or you can look at it as, okay, that molarity is going to cancel with one of those molarities, and I have 1 molarity left on the bottom, and I still have the time left on the bottom. Okay, so notice that the way that they write it as, after they do the math, it's 8.00 times 10 to the third, and then you've got a molarity and a second left on the bottom. That is correct. There's no unit left on the top. There's only numbers on the bottom. And the way that you can express that is by writing molarity to the -1 or seconds to the -1. Okay, many times with example with R, with the gas constant, it's 0.08206 liters atmospheres, and then they'll write Kelvin -1, moles -1. And again, what that means is that the Kelvin and the moles go on the bottom. Same thing here, the molarity and the seconds actually go on the bottom. Okay, so the units vary a great deal depending on what the order is. For example, if this were just a first order reaction instead of a second order reaction, well, if it's first order, then there's only one of those reactants. Then both molarities cancel, and what are you left with? You're just left with the time to the -1. Okay, it's always time to the -1. It's just how many molarities are there. Okay, let's pretend, for example, that this was third order. Let's say this one was molarity squared. Okay, let's say that was a second order, like the order was second with respect to A or B or whatever it was. So now you've got molarity cubed on the bottom. Well, then that molarity is going to, again, cancel with one of those molarities, and you're going to be left with molarity to the -2, and then seconds to the -1. Okay? So the easiest way to do that, which again I know is difficult for students, is write out your units. Write out all of your units so you can see, oh, if I have a molarity on the top and on the bottom, it cancels. Whatever units are left, that's what has to go in my answer. Okay, so example 1 says verify the value of the rate constant from example 1 above using the data from trial 1 to calculate the rate constant. Include units with your answer. So if we use the information from trial 1 from example 1, then again we've got our rate is 1.00, and then we've got an initial concentration of A2 of this and of B2 of that. So we're going to set it up, and we're going to just solve for K. And remember, they were both, here's our rate law right here. So we're going to use that rate law to find the value of K. And again, in my example, I use the information from trial 2. Theoretically, if our rate law is correct, it doesn't matter which trial we use. We should get the same result. So our rate is 1.00 molarity per second, and that equals K. So I'm just filling in the rate law here, right? Just like here, I'm just putting everything in there. And then we're going to multiply it by the concentration of A. Now, at this point, when you're putting the actual numbers in, you don't need to use the square brackets. When we're saying the concentration of something, you must use square brackets. But when you're actually putting this 0.005 and 0.025 in there, you don't actually have to do that. So it's 0.005, I think there are a couple of zeros after that, and 0.025. And now we just go to the calculator. Now we solve for K. And again, this is molarity, this is molarity. So K is going to equal 1.00 molarity per second. See how I do that? Over 0.005 molar times 0.025 molar. And those molarities are going to cancel. And then I come to this and I go 1 divided by 0.005 divided by 0.025. And that, of course, equals the same number. Okay, 8,000, which is the same thing as this. I just, with 3 significant figures, I put it in scientific notation. Okay, and then I have a molarity left on the bottom. So that's molarity to the -1 seconds to the -1. Okay, and then for example 2, says determine the value of the rate constant from example 2 above. Include units with your answer. So here's where you pause. Go ahead and pause the video. Go back up to any of those trials from example 2 and see if we end up getting the same answer. So I'm going to use, just because it's the first one, I'm going to use the data from trial 1. So the rate was 10 molar per second. So I'm going to start with that, 10. And if you use a different one, good. Hopefully we end up getting the same answer. And again, I'm kind of looking at my rate law here as well. And I remember that the concentration of H plus, remember, was second order. That's the only thing we really got to pay attention to. So the BrO3 minus is 0.0050. So K times 0.0050 molar times, and then Br minus is 0.025 molar, and then the H plus, I think it was 0.030. Let me just verify that. Yeah, 0.030. Okay, so from trial 1, 0.030 molar, close parentheses, then square it. So those molarities inside of there are squared. Okay, so now to solve for K, K is going to equal 10 molar per second. And I just kind of put it down at the end just so I can have plenty of space. 0.005, and I'm going to leave that last zero off. And then 0.030 molar squared. Okay, and then I'm going to type that into my calculator. So I get 10 divided by 0.005 divided by 0.025 divided by 0.030 squared. And I get an answer, let's put that in scientific notation, of 8.89 times 10 to the 7th. And then in terms of units, molarity and molarity cancel. So I've got a molarity on the bottom and another molarity squared on the bottom. So I've got molarity to the -3, and then still seconds to the minus 1. Okay, and that is kind of an introduction there to the rate constant. Let's talk about this, and then we'll talk about some other challenging problems here. So, at the beginning of the unit, we talked about how if you increase the temperature, that does not affect the activation energy. Okay, but what it does do is it gives more molecules enough energy to overcome the activation energy barrier. Okay, but when you look at a rate law, you're like, well, wait a minute, rate equals K times the concentration. Wait a minute, where's temperature in there? There is no temperature in there. Okay, so how can temperature affect the rate? Because the rate constant changes with temperature. An increase in the temperature causes the rate constant to increase and vice versa. Temperature goes down, the rate constant goes down. Okay, this occurs because as the temperature increases, the kinetic energy of the particles also increases. We know the particles collide more often and with more force. Okay, we've already learned that. Notice that a change in the reactant concentration, however, does not affect the value of the rate constant. Okay, which means if you change this or you change this, that does not change this at all. They try to trick you with questions like that. Okay, changing the concentration. The only thing that changes the rate constant is temperature. That's what you need to remember. Okay, only a temperature change causes the value of the rate constant to change. Another way of saying it is if the temperature increases, the rate constant increases, and therefore so does the rate of the reaction. Okay, obviously if this number gets bigger and these don't change, of course the rate has to go up. Okay, if a reactant concentration increases though, then of course the rate will also go up as long as it's not zero order, but of course the rate constant will not. Okay, so when this gets bigger, these don't change, but of course this does. And likewise, when these get bigger, this doesn't change, but of course the rate does go up.